As soon as we hit 88 kilometers per hour, the flux capacitor kicked in and... In the previous episode, we got our diesel Saturn semi-roadworthy. However, we did discover a problem, and that is the car would only go 45 miles per hour. Getting the car up to 45 miles per hour took all of 1 minute and 3 seconds. Well, we sort of knew the car was going to be slow, but that was completely unacceptable. Today we're going to make the car go a lot faster, and we're going to check the fuel consumption of the little Kubota engine. But before we do any testing, we still have a few things we need to do to make the car more roadworthy. Before we get started, let's take a look at the before and after weight of the Saturn. Now, prior to the engine swap, we took the car over to the farmer's co-op and had it weighed. With a full tank of gasoline, our little red coupe tipped the scales at 2,280 pounds. After we replaced the 1.9-liter gasoline engine with a 722cc diesel engine, well, the weight of the car dropped at 2,080 pounds, and that calculates to a difference of exactly 200 pounds. So how much of this difference is from the engine transplant? Let's find out. If you recall, the car had a full tank of gasoline, and since this is a diesel swap, we won't be needing the gasoline. Anyway, with 12 gallons of gasoline at 6 pounds per gallon, works out to 72 pounds of gasoline, or petro. Now, we didn't stop there. We also removed the fuel tank, and that lightened the car an additional 18 pounds. And that gives us a grand total of 90 pounds in weight savings. Well, not quite. You see, we installed a smaller fuel tank and topped it off with 4 gallons of diesel fuel. So the new tank with the fuel added 20 pounds back to the car. So in total, we removed 70 pounds. Now, on the inside of the car, we looked around for stuff we could remove, and the only thing we could find was the non-functional radio. So we pitched that overboard, and that got us an additional 2 pounds of weight savings. So after we did a bit of calculations, it was determined that out of the 200 pounds difference before and after the engine swap, 128 pounds of that difference was from the little diesel engine being lighter than the Saturn engine. So the first thing we need to get working on our little engine is the 20 amp alternator. Now, we're very familiar with this type of alternator and have used it with great success on our street legal go-kart. We even dedicated a whole video to this alternator and other alternator options back in Season 2, Episode 4. So this Saturn was originally equipped with a 90 amp alternator to provide the juice for the headlights, the air conditioner, the rear defroster, the windshield wipers, and other stuff. If we were building a daily driver, we would probably need to use a big alternator like this one. However, there is a penalty for running such a big alternator, and that's the horsepower it absorbs from the engine in order to generate the current required for a full load. A 90 amp alternator like this one can absorb close to 3 horsepower from the engine. Now, the math used to calculate how much power the alternator absorbs is not exactly straightforward, because you also have to factor in the efficiency. Now, typically alternators are about 60% efficient. Anyway, the 20 amp alternator absorbs less power from the engine, but also supplies significantly less juice to the accessories. Since this car is just a test vehicle and only driven on dry and sunny days, we only need a few amps to power the gauges and the electric fuel pump. And of course the brake lights and occasional turn signals. Now keep in mind, the headlights, wipers, and everything else still work, but we just won't be using them. Like I mentioned before, we've used this 20 amp alternator on a previous project with great success, and there's a video on how it works. But we'll give you a quick overview on how it's connected. The 2 blue wires from the alternator connect to the blue wires on the regulator. Since these wires supply AC voltage, the polarity doesn't matter. The black wire from the regulator gets grounded to the chassis of the car, and the red wire goes directly to the battery or the 12-volt main terminal on the fuse box. This wire should be as short as possible because it carries the full 20 amps. The yellow wire goes to the ignition switch, and this is what turns the regulator on. The green wire goes to an idiot light, and on this regulator setup, the green wire connection isn't necessary as the regulator will work fine without the idiot light. But that's not always the case on other charging systems. Most of the time, the idiot light's required for the charging system to work properly. Let's take a look at the completed system. So we ended up mounting the regulator on a custom aluminum plate near the underhood fuse box. The red wire connects to the 12-volt terminal on the fuse box, and this heavy gauge wire is also connected to the same spot. Now this heavy gauge wire connects directly to the battery in the trunk. The yellow wire connects to an unused fuse, and whenever the ignition switch is turned on, this fuse gets power, and in turn it activates the regulator. It's a simple system, and will provide just enough juice to keep the battery charged with the limited power draw on this test vehicle. Let's take a look at the cheapest tachometer we could find for this diesel engine. So this tachometer is intended to be used on industrial equipment like a drill press, a lathe, a mill. It's a cheap way to measure the spindle speed on various machines. We got it from the Jungle site for $19, and that's with free shipping. Yeah, this tachometer was cheap, but more importantly, it'll be visible to the camera when we do performance testing. A few people suggested that we could easily get the gauges to work again on the Saturn's dashboard, and I appreciate the tech advice. I reckon that's something we would do if we were building a daily driver. However, for these videos, we're going to go with instruments that can be seen by the camera. Anyway, this tach is super simple to hook up. It even comes with a little harness. The red wire is 12 volts, the black wire is ground, and the yellow wire is for the signal. This kit comes with a giant magnet that you're supposed to glue to the spinny part that you want to measure shaft speed of, and we'll get to that in a minute. This is the proximity sensor that comes with the kit. This sensor is actually a Hall effect sensor, and it detects magnetic fields. Of course it comes with instructions. Now a lot of folks like to point out the spelling mistakes that somehow get past our editor, and here's one for you. But we can't take credit for this one. Nope, we have to give credit to the manufacturer of the tachometer. So the magnet that comes with this kit is way too big for our application, and we're going to use a smaller magnet. It'll all make sense in a minute. Let's bench test this thing and see how it works. The Wago type connectors that I'm using are for splicing 3 independent circuits and is not a bust connector. These are great for bench testing stuff as they allow for quick connections. The wire color code on the proximity sensor is standard for industrial wiring, but it's a little confusing for automotive wiring. Alright, let's power this up. Now, according to the documentation, this tach works fine between 8 and 24 volts, so it'll have no problem with the voltages in the car. So far, so good. Now, if we move the magnet past the sensor, we should get some kind of reading on the display. The polarity of the magnet makes a difference. Almost all industrial proximity sensors are configured to trigger when exposed to the south pole of a magnet. If you use the north pole of the magnet, the sensor won't trigger at all. Anyway, it looks like we triggered the sensor and we got some garbage readings on the display. This is actually normal when bench testing. Let's attach this magnet to the drill and see if we can measure the speed of the chuck. Oh, by the way, this display has an annoying feature, and it'll display the last known RPM for a few seconds after the signal's removed. I reckon this annoying feature makes sense if you're using the tachometer for the application it was intended for, but in our case, it's just annoying. Now, the sensor needs to be about 2 millimeters from the magnet, otherwise it won't trigger. Meh, good enough. Let's make this work on the engine. So to measure the RPM on the engine, we're going to modify the crankshaft pulley by drilling a hole in it and inserting a magnet into the hole. According to the documentation, this tachometer can measure up to 9,999 RPM, so that'll be more than adequate for this engine. A quick trip to the Smithy 3-in-1 lathe, mill, and drill press combo, and we have a perfectly drilled hole in the crankshaft pulley. Let's see if the magnet fits. Now, this is just a test fit. Normally, we would insert the magnet with the south pole facing out, and at this point, whatever pole's facing out is random. Now, before the magnet is staked into place, I ran the sensor over the magnet to confirm the south pole is facing out. On this setup, you can see the LED dim a little bit when it senses the magnet. Apparently, this is normal. I was sort of expecting the LED to turn completely on or off, and I find this to be disturbing. However, after some research on the tachometer, apparently this is how the manufacturer intended it to work. Anyway, once the polarity of the magnet was confirmed, I went ahead and staked the magnet into place using a center punch. For extra security, we mixed up some JB Weld and added a layer of epoxy on both sides of the magnet. For this, we're using slow setting JB Weld. I'm not a big fan of the quick setting stuff. Now, I have no proof, but I feel the quick setting stuff is not as good as the slow stuff. Anyway, that's my opinion and I could be wrong. Future Jimbo here. Let me interrupt this idiot for a moment and talk about something completely different. This mark on the crankshaft pulley has to line up with a similar mark on the crankshaft. Otherwise, the engine will be unbalanced. Okay, on this picture, you can see the two marks are lined up, and this is correct. So if you ever remove the crank pulley on a Kubota engine, make sure you put the pulley back on the engine correctly. Alright, let's get back to watching this guy slather JB Weld on the pulley. Oh joy. At some point you have to ask yourself, how much JB Weld is enough? I mean, I could keep going, but this seems to be enough. Once this stuff cures in 24 hours, we'll clean it up with a bit of sandpaper, then put it back on the engine. Off camera, we built a bracket from 1/8 inch mild steel to hold the proximity sensor in place. This bracket was extremely hard to fabricate, and it ain't perfect, but it should work fine. Give me a minute to install the bracket on the engine, and we'll have one last look at it. Here's the bracket mounted on the engine. So basically our $19 tachometer was a bit more complicated than we expected. I'll say this bracket would have been a breeze to build when the engine was still out of the car. So as we move forward with this build, we're ending up with buttons on the dashboard that no longer work. For instance, the air conditioner and the recirculation button are no longer needed, or are they? We took the button pod out of the car and modified it slightly to repurpose it. The latching mechanisms on the buttons were removed, so now the buttons have been modified to be momentary push buttons. The button that previously engaged the air conditioner will now be our glow plug button. The recirculation button, well, we don't have a purpose for it yet, but I'm sure we'll find one. Both buttons are wired, but for now, we'll only be using one button. Let's fast forward a bit and see how all this stuff works. We 3D printed a custom holder for the GPS speedometer and the $19 tachometer. This holder will put the speedo and the tach in a good position for the camera when we do our road tests. The speedometer needs 5 volts to work, and we power it from this battery bank. Anyway, since the tach is 12 volts and we don't have to wait for it to boot up, it gets powered directly from the ignition switch. Let's start the engine and see if the tachometer and the alternator work. Oh yeah, we connected the diesel engine to the exhaust system on the Saturn. This makes a huge difference, as you can probably guess. So the diesel engine's cold and the idle tends to jump around a bit, and we can see that on the tachometer. Let's check the alternator. Well, at idle, the alternator doesn't seem to put out much of a charge. Well, at 2000 RPM, it puts out a little bit more of a charge, but I have to say it's not much. It may be that the battery's a bit low and the alternator's having trouble keeping up right now. We'll have to keep an eye on this. So in the previous video, we got the car to go 45 miles per hour flat out. And after doing some calculations, we determined that the engine governor was maxed out at 2800 RPM. Let's see how true that is. Well, we were close. The engine is capped at 2700 RPM. Now that little shudder when I released the throttle is from the crankshaft pulley being installed incorrectly. We eventually figured this out. Perhaps I should tell future Jimbo and he'll give us a heads up. Anyway, if we want to get to 60 miles per hour in 4th gear, we'll need to adjust the governor to max out at 3800 RPM. Adjusting the governor is pretty easy and only requires backing this screw out. Let me do that off camera, then we'll check the tachometer again. Yeah, it looks like we got it. Actually, after we filmed this bit, we backed the screw out all the way. We're not exactly sure what the max engine speed is now, but it's definitely a lot higher than 3800 RPM. So the last thing we need to fiddle with is the thermostat. In the previous episode, the engine would not generate any heat if we blew air across the radiator. Normally, blowing air across the radiator should not affect the engine temperature because the thermostat keeps the coolant from circulating to the radiator. Now, when the thermostat opens, then the air blowing across the radiator should make a difference. But until the thermostat opens, the engine should be able to generate heat. Well, the thermostat we took out looked fine, and we put it back in and tested it again, and it still didn't work. So then we bought another thermostat, and this one was rated for 180 degrees Fahrenheit, and the previous one was rated for 160 degrees Fahrenheit. Anyway, this one didn't work either. So somehow coolant's getting past the thermostat. That's the only thing that makes sense. So this time around, we decided to glue the thermostat into place with Honda Bond. This stuff will seal anything. So basically, we smeared Honda Bond all over the thermostat housing and then installed the thermostat and associated parts. Well, that didn't work either. It turns out that this tiny bypass hole in the thermostat is enough of a coolant leak to keep the engine from developing any heat. We spent a lot of time fiddling with the thermostat in order to get the engine to stay hot, and this was the problem. Anyway, now that we're making heat, we decided to connect the cooling system to the heater core in the car so we could keep the cabin warm during our road tests. Well, as you can imagine, the heater core will suck the heat right out of that engine pretty quick, So it's kind of a balancing act of sorts, and we ended up covering much of the radiator with a slab of cardboard. At this point, the part of the radiator that is exposed to the airflow is completely covered, and the radiator pretty much doesn't do anything. It took a lot of testing to get this to work, and the few seconds you see on video actually took days to sort out. So now we have a working alternator, and that's highly debatable, but we're going to go with it. A working tachometer, a decent heater, a full exhaust, the engine governor's maxed out. What else? Put the hood on the car! Okay, now what?
Road test!
Okay, I thought you would never ask. Perhaps out of morbid curiosity, we get new viewers to this channel every time a fresh video drops. So for the folks that are seeing this project for the first time, keep in mind this is a work in progress, and the data we collect today will help us improve the car. But there's only so much we can do. The diesel engine that we're using is only 719 cc's and makes a mere 20 horsepower. Now we do have plans on adding a turbocharger to boost performance, but before we do that, we have to collect data. So now we're heading out of town, and I'm running the engine as fast as it will go in each gear. This car doesn't simply accelerate. Instead, it moves forward and slowly increases in speed. You don't get any sense that the speed is increasing other than what's displayed on the speedometer. Looks like the engine's having trouble picking up speed on the top end. Now, if you recall, we backed the governor off completely, so this is interesting. So it looks like 59 miles per hour is the fastest this thing can go. Now we're only showing a few minutes of the road tests that were done, but in reality we put over 300 miles on this car in the past 2 weeks. 59 miles per hour is pretty much it, but we did get the car up to 63 miles per hour on a few occasions, and that's likely due to a tailwind. Overall, the engine seems to have enough power to keep the car consistently at 55 miles per hour. Anyway, the rule when driving this car is never slow down if you don't have to. Now it's cold today, and thankfully the heater's keeping the car very comfortable. The blower speed is set to 1, and that both reduces the power the blower draws and allows the engine to stay hot. I reckon a lot of folks are interested in the fuel economy this car gets. Keep in mind, we didn't build this car for fuel economy, but it's an interesting data point. I have mixed feelings on how well this car will do. I feel the engine is too small and is working way too hard to propel this Saturn down the road. Anyway, that's my opinion, and we'll certainly find out soon enough. The close ratio transmission helps the little diesel engine accelerate this 2,080-pound car up to speed. So far, we've shown you how the car performs in first through fourth gear. Let's see how it does in fifth gear. Alright, now we're in fifth gear. And the car's slowing down. Yep, we simply don't have enough power to keep accelerating in fifth gear, and we can blame that on aerodynamic drag. For the record, let's do an official acceleration run up to 55 miles per hour or 88 kilometers per hour. On this run, we'll mark every time the car increases speed by 10 miles per hour with a beep. This was top speed last time we did the test. As soon as we hit 88 kilometers per hour, the flux capacitor kicked in and we were transported back to 1955. But that's a story for another video. Anyway, we headed back to the shop, refueled the car, and did a fuel economy test. Let's take a look at the data. In the previous video, we recorded a top speed of only 45 miles per hour. Now, after adjusting the governor, the top speed was increased to 59 miles per hour. At this point, it's not the governor that's slowing us down, it's the aerodynamic drag and a lack of power. Alright, acceleration. Well, if you haven't guessed by now, this car is definitely slow. With the governor maxed out, we got the car up to 55 miles per hour in 1 minute and 6 seconds. If we look at the data points during the acceleration test, we can see the car loses momentum the faster it goes, and the time between data points increases. It's interesting to see how the wind resistance has a profound effect on a car with limited horsepower. Now, these results might be obvious for some folks, but keep in mind experiments like this provide a better understanding for people who may not have an automotive background. Let's see how the car did as far as fuel economy goes. So due to the smaller fuel tank, we really weren't sure how far the little diesel engine would take the car, so we limited the experiment to 85 miles. Now for this test, we tried to keep the car at 55 miles per hour, which is kind of tough to do. Sometimes it wanted to go faster, and sometimes it wanted to go slower. Anyway, we consumed 1.5 gallons of fuel, and that works out to 56.66 miles per gallon. I have to say that's a lot better than I thought the car would do, and I sort of expected something in the low to mid 40s. Just to confirm the results, we went back out and did the test again and got 56.50 miles per gallon. I think it's fair to say that our results are consistent. So a few things to consider when evaluating fuel economy. It's winter here in Kansas, and it's been a bit on the cold side lately. We ran both fuel economy tests with the car in 4th gear, and the engine was chooching about 3,200 RPM. Now, 4th gear is certainly not ideal, but remember this car can't handle 5th gear, and that's due to not having enough power to fight the aerodynamic drag. I think the car did great, but there may be room for some improvement. Anyway, if you made it this far into the video, thank you for sticking around. As you know, this project is far from over. Today's test results will give us a good baseline to work with, and now is a good time to consider subscribing if you haven't already. It'll definitely be interesting to see how much we can improve the performance of this car with the little diesel engine. Until next time.